Alright, this is a lesson on calculating limits, and we're going to learn how to calculate limits from both equations and graphs. So when you're ready to start this lesson, make sure you head on over to jensenmath.ca so you can get a copy of the lesson. We are in the Advanced Functions course. We're in the 6th unit on rates of change, and we are on lesson 5, limits and discontinuity. So you can get a blank copy of the lesson here, and after the lesson you can get some practice problems here at the student worksheet. And after you try the practice problems, you can check your solutions here by clicking on Worksheet Solutions. So when you're ready, let's get started. So we're going to start this lesson by looking at the concept of a limit through the lens of how Archimedes discovered the formula for the area of a triangle, area equals pi r squared. Use something called the method of exhaustion. So feel free to pause the video right here and read this whole section. But what I'm going to do is I'm going to go over to an app in GeoGebra where I can kind of demonstrate this to you to make sure you get the idea about this method of exhaustion. So what I have here is a circle. And this circle, I've made its radius be 1. So a circle with radius 1, well, its area, we know its area, would just be pi, right? Because we know the formula for the area of a circle is pi times the radius squared. So pi times 1 squared is just pi. So the area of this green circle is just pi. But back in the day, people didn't know how to find the area of circles, but they knew how to find areas of polygons. So what they did was they inscribed polygons inside of the circle and found the area of those polygons, and then figured, okay, well, the area of the circle is somewhat close to the area of that polygon that's inscribed inside of the circle. But then they thought, okay, well, this 3-sided polygon clearly doesn't fill that whole circle, so maybe if I add another side, maybe if I make it a 4-sided polygon, oh yeah, that does fill the circle quite a bit more. This 4-sided polygon is a better representation of the area. Well, if a 4-sided polygon is better, a 5-sided polygon would be even better. And notice right here I have it showing you the area of the inscribed polygon. We know the area of the circle is pi. Right now the area of the inscribed polygon is 2.38. Still quite a bit less than pi, that 3.1415 value. But it's better than what it was when we just inscribed it with a triangle. When we inscribed it with a triangle, the area of the triangle was only 1.3. The area of the 4-sided polygon was 2. The area of the 5-sided polygon was 2.38. So you can see where I'm going with this, right? The more sides we add to this polygon, the closer the area of that polygon is to the area of the circle, pi. So what we're looking at is something called the method of exhaustion. Well, why don't we just add an infinite number of sides to this polygon? The more sides we add, the more it fills the area of the circle, and the closer the area of the polygon gets to the area of the circle. You can see that we're really closely approaching 3.14. So theoretically, if we could have a polygon inside with an infinite number of sides, if I could let the number of sides of the polygon approach infinity, what would the area of that polygon be approaching? And that would tell me what the area of the circle is. So you can see that as this number of sides is getting bigger, as it's approaching infinity. Imagine having a polygon with 1,000 sides. What do you think this area value would be approaching? You can see that it's approaching about 3.14 if I were able to add more sides onto that inscribed polygon. So what I've just talked to you about is limits. I've talked to you about how if we let the independent variable go towards a value, so if we let the number of sides go towards infinity, what's happening to the dependent variable? What's happening to the area? What's that getting close to? That's the idea of a limit. So if we could find the limit of the area as the number of sides goes to infinity, we could figure out the area of that circle using areas of polygons. And we'd figure out the area of this circle with a radius of 1 is actually just pi. Okay, now that I've introduced you to the idea of a limit, let's do an example here where we get to understand the notation for limits. So like I said, when we do limits, we're going to be letting the independent variable x go towards a certain value, and then figure out what are the y values trending towards as the independent variable goes towards a certain value. So what we have here is the function x squared minus 2. So our function is y equals x squared minus 2. We're going to calculate a few limits for that function x squared minus 2. And this notation here, let's focus in on here. This says find the limit of the x squared minus 2 function. So find the limit of the y value as the x value approaches 3, and then this little minus sign here written as an exponent is very important. That means from the left of 3. So if you think of a number line, it means as x approaches 3 from numbers less than 3. And this one here says, what is the limit of x squared minus 2 as x approaches 3 from the right side of 3, so from numbers that are bigger than 3. And then we can use this table up here I've created to help understand what I'm talking about from the left, from the right, and what's the limit of x squared minus 2 as x approaches 3. So let's evaluate this first limit. So keep in mind, we're finding the limit of the x squared minus 2 values, these are the y values, as the x values approach 3 from the left. So from this table, I have x values at the top here. These are independent variables. I put 3 in the middle. We're interested in what is happening to the x squared minus 2 values as x approaches 3 from the left. So that would mean from over here. So as I approach 3 from the left, well, what's the value of x squared minus 2 when x is 2? If we plug 2 into this equation, 4 minus 2 is 2. How about when x is 2.5? If I plug 2.5 in this equation, I would get a y value of 4.25. If I plug 2.9 in, I get a y value of 6.41. And if I plug 2.99 in for x, I get a y value of 6.9401. So you can see, what are these values look like they're getting closer and closer and closer to. I don't care what it is when x is 3. I'm just interested in what are the y values getting close to. What are they approaching as x approaches 3 from the left of 3? So from this side. What are these values trending towards? The x squared minus 2 values look like they're trending towards 7. So I would say the limit of x squared minus 2 as x approaches 3 from the left is 7. And if I were to plug 3 into this equation, it actually does equal 7. But when we're doing limits, we don't actually care what it equals at the point. We just care what is it approaching as we get close to that point. Okay, how about if we do it from the other side? If we find the limit of the x squared minus 2 values as we approach 3 from the right side of 3. So from the right side of 3 means x values that are bigger than 3. So here's some x values that are bigger than 3. And then let's approach 3 from the right side of 3. And let's see what's happening to the y values, the x squared minus 2 values, as the x values approach 3 from the right side of 3. If I plug 4 into this equation, I would get 14. Plug 3.5 into the equation, I would get 10.25. Plug 3.1 in, I get 7.61. Plug 3.01 in, I would get 7.06. Notice these y values, these x squared minus 2 values, as the x values are getting closer to 3 from the right, it looks like these y values are approaching 7. So there's that whole table filled out for you. Let me just give you a graphical demonstration of what we just did, because I think maybe that will help your understanding of this as well. So this red function is the x squared minus 2 function. And I have Desmos letting me drag a point along where that point shows me the x and y coordinate at any point. And we're interested in the limit as x approaches 3 from the left and from the right. So what I did was I drew a vertical line through an x value of 3, just so you can see what we're approaching. So as we let the x values approach 3 from the left side of 3, so notice that this dot is to the left of that vertical line, x equals 3. As I drag this dot closer to an x value of 3 from the left side of 3, pay attention to the y values. What do they look like they're getting close to? That's what we're doing. We're finding the limit of the y values as the x values get closer to 3 from the left side of 3. So right now the x value is at 0. I'm going to move that x value closer to 3 and then pay attention to what's happening to the y values. the y values, and you can also see the y values here. The y values, as I move this point closer and closer and closer to an x value of 3, from the left of 3, the y values are going up, up, up. They're at 4, 5, 6, 6.5, 6.7, and the y, let me get the x value to like 2.98. Okay, notice the y value is at 6.88. As this point, as the x values of that point are getting closer and closer to 3, the y values look like they're getting closer and closer and closer to 7. How about from the right side? So let me bring this point to the right side of 3. So if we find the limit of the x squared minus 2 values, so the y values, as x approached 3 from the right side of 3, so as this x value gets closer to 3, what's happening to the y values? What are the y values getting close to? It looks like they're also getting closer and closer and closer and closer and closer to 7. Right? From either side, we're approaching the point 3, 7. I've added in that green point on the function. That's where the function is when x is 3. From the right side of 3, if we approached an x value of 3, we would be approaching that point, so we would be approaching a y value of 7. And from the left side of an x value of 3, if I approached an x value of 3, the y values would be approaching the y value of that green point, 7. So hopefully that helped you understand these limit expressions. And if the limit from the left and from the right of a certain x value are the exact same and they both exist, we can conclude that that is the limit of x squared minus 2 as x approaches 3. So a general rule, we can only say a limit of a y value of a function exists if 3 criteria are met. The limit from the left exists, the limit from the right exists, and the limit from the left and right are equal to each other. If the limits from the left and right do not equal each other,
if the limit never approaches anything, the limit does not exist. The limit does not exist!
We say the limit does not exist. Alright, in example 2 here, we're finding a limit from a graph, and this is the graph of a piecewise function. It's made up of 3 functions in different parts of its domain. So when x is less than 1, it's a linear function x minus 1, so it's this part of the function right here. And then at an x value of 1, it's just equal to 1. It's just a point right here, the point 1, 1. And then when x is greater than 1, it's this radical function, looks like that. So that is our piecewise function. It's made up of those 3 parts. Using the graph of that function, let's write some limits of that function. So when you see f at x, think y value. F at x is just function notation for the y value at a certain value of x. So we're interested in what's the limit of y values as x approaches 1 from the left of 1. So let me go to Desmos to give you a better picture of the graph where we can slide a point along it. So here's the graph. Once again, I have Desmos showing me the x and y coordinates of any point along this function. What I want to do first, I want to find the limit of the y value, so pay attention to the y value, which I have Desmos showing us here as well, as the x value gets closer and closer to 1 from the left side of 1. So maybe it'll help if I draw on that vertical line at 1 again. So as I get closer and closer and closer to that vertical line, from the left of that vertical line, what does it look like the y values are getting closer and closer and closer towards? It looks like the y values are getting closer and closer and closer to whatever the y coordinate of that hollow dot are. Remember, that hollow dot means the function's not there. A filled in dot means that's where the function is. So the function's actually up here. But as I approach an x value of 1, it's not taking me to that dot. It's taking me to this open dot. So the function isn't actually there, but that's where the limit is taking me. As x gets closer to 1, the y value is getting closer and closer and closer and closer to 0, the y value of that open dot. So the limit of the y values as x approaches 1 from the left is 0. From the left, it's approaching that open dot. And that open dot has a y value of 0. How about if I approach an x value of 1 from the right of 1? What's happening to the y values? What are they approaching? So let's now move our dot over here. That's to the right of an x value of 1. Pay attention, what are the y values going towards? The y values are going towards, it looks like they're going towards, right now they're at 2.3, now they're at 2.2, now they're at, well, 2.2 exactly, Let's see if I can get one more. Now they're at 2.1. Look, it looks like it's going towards a y value of 2. As I approach an x value of 1 from the right, I'm approaching that open dot right there, which has a y value of 2. So the limit from the right, so the limit of the y values as I approach 1 from the right is 2. As I approach 1 from the right, as I trace along the function, the y values are getting closer and closer to the y value of that open dot. Now the function isn't there when x is 1. The function is actually here. But that doesn't matter. When we do limits, we don't care where the function actually is. We just want to know what is it approaching as we get closer and closer and closer to the given x value. So since the limit from the left and the right both exist, we've met the first two conditions here. But the third condition says the limit only exists if not only do the left and right limits exist, but they're also equal to each other. Well, 0 and 2 are not equal to each other. So we say the limit of f at x as x approaches 1 does not exist. Okay, example 3, same type of example, just different function. We're finding limits from a graph again. Let's find the limit of the y values of this function, x plus 1 over x minus 4, as x approaches 4 from the left of 4. And I have the graph of this function shown to you here. It actually has two asymptotes. I should draw in the horizontal asymptote. It has a horizontal asymptote at y equals 1. And it has a vertical asymptote at x equals 4. So the function doesn't exist when x is 4. But that doesn't mean the limit doesn't exist. We don't care what is happening at 4. We just care what's happening as we approach 4. So once again, let's go to Desmos where we can do a little bit of sliding of the point. So the first limit it asked us to calculate was the limit of the y values, so the limit of these x plus 1 over x minus 4 values, as x approaches 4, and there's a vertical asymptote there, so that's nice, I can approach that, from the left of it. So as I approach that vertical asymptote from the left of it, what's happening to the y values? Well, the y value is at like -1, now it's at -2, now it's at -3. And let me zoom out a bit here, just so we can see more. As I keep going, this point's just going to keep going down and down and down and down. It's going to go infinitely down, right? What do we know about asymptotes? We know the function's going to get closer and closer and closer and closer to that asymptote, but it'll never get there. So like, what if I put in, so okay, I have the y values being calculated here. What if I put in an x value of 3.5? I'm at a y value of -9. How about 3.9? That's even closer. Okay, whoa, the y value went way down to -49. How about 3.99? The y value is -499. Can I zoom out to see that? Okay, whoa, there's the point way down there. How about 3.999? And then just keep adding 9s, keep getting closer and closer and closer to an x value of 4. And look, this number is getting closer and closer and closer to negative infinity. This is -4.9999 times 10 to the power of 10. It's an extremely big negative number. So it's going towards, my conclusion, it's going towards negative infinity. How about if I approached an x value of 4 from the right? What's happening to the y values? Alright, so I've moved the point to the right of an x value of 4, right? 7.93, we consider that to the right of 4. If I now move this point closer to 4, what's happening to the y values? They're going up, 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 and they're going to keep going up and up. Let's get even closer. Right now, 4.7. Let's get even closer to 4 from the right of it. So like 4.2. The y value is now 26. How about 4.1? The y value is now 51. How about 4.01? The y value is 501. And keep adding in zeros here. And notice the y values are just going up and up and up. They're going off to positive infinity. So the limit of the y values as x approaches 4 from the right side of 4 is infinity. So since these two limits are not the same, we say the limit as x approaches 4 does not exist. And this should be obvious it doesn't exist because, look, from the left side of 4, the function's going down here. From the right side of 4, the function's going here. It's clearly not going towards the same point, so the limit does not exist. Alright, this example is very similar to the last one we did, but instead of there being an asymptote, the restriction on the function actually shows up as a hole in the function. So let's look at how that affects our limits while we're calculating them. So here's the equation of the original function. F of x equals x squared minus 1 over x minus 1. We're going to find the limit of the y values of that function as x approaches 1 from the left, from the right, and then the overall limit as x approaches 1 of the function. So I actually have a table filled out for you here to help you see what's happening. So as we approach an x value of 1 from the left, what's happening to the y values? Well, here's a row of the y values, and here's a row of the x values. So as I approach an x value of 1 from the left side of 1, what do you think these y values are approaching? It looks like to me they're going from 1 to 1.5 to 1.9 to 1.99 to 1.999. It looks like they're going to 2. I don't care what the y value is at 1, I just care what are the y values approaching as I get closer and closer to an x value of 1 from the left. Okay, how about if I approach 1 from the right side of 1? What's happening to the y values? These y values, from 3 to 2.5 to 2.1 to 2.01 to 2.001, it looks like to me they're approaching 2. Let's look at the graph to verify what we just talked about. So we won't bother going over to Desmos for this one. I'll just drag this dot I made around on here. So as I approach an x value of 1, here's an x value of 1. So as I approach an x value of 1, what's happening to the y value of the function? If I approach an x value of 1 from the left, the y values look like, well, it looks like the function is going towards that open circle. And that open circle has a y value of 2. How about if I approach an x value of 1 from the right? It looks like the y values are going towards the y value of that open circle, which is 2. So hopefully you can see the limit as we approach from the left and from the right of the y values is 2. So what do we conclude? Well, the limit from the left exists, the limit from the right exists, and the limit from the left and right are equal. So we can say that the limit of the y values as x approaches 1 is equal to 2. Now the function doesn't actually exist there. When x is 1, the function is undefined. If you don't believe me, plug 1 into this equation. We get 0 over 0. But that doesn't matter when it comes to limits. We don't care where the actual function is when x is 1. We just care what was it approaching from either side of 1. So this is what I just mentioned here. When we plug x equals 1 to the equation, we get 0 over 0. That's called indeterminate form. 0 divided by 0 is undefined. However, it's not necessary for the function to be defined at a point for the limit to exist. That's what I've just talked about. When we get 0 over 0, we know there's a hole in the graph, and it's very possible that from either side of that hole, the function is approaching that same point. So watch what I mean algebraically. Okay, so our f of x function was x squared minus 1 over x minus 1. So really what we're finding is the limit of the value of that as the x value approaches 1. This can be simplified. So let me just keep writing the limit statement, and I'll tell you when we can stop writing it. So the limit as x approaches 1 of this would equal the limit as x approaches 1 of this in factored form. So x minus 1 times x plus 1. It's a difference of squares in the numerator. And now I have a factor of x minus 1 here and here. Anything divided by itself is 1. Well, not anything, right? 0 divided by 0 isn't 1. So I can only cancel this if I'm sure I'm not canceling out 0 over 0. Well, I can actually be sure I'm not doing 0 over 0 right now. How can I be sure? Well, the only way that both of those factors would be 0 is if x was 1. And what are we finding? We're finding the limit as x approaches 1. So the only value I can guarantee we're not plugging in for x is 1. So since we're only finding the limit as x is approaching 1, I can cancel those out. Anything divided by itself is 1. And what we're left with is the limit as x approaches 1 of the function x plus 1. I've now removed those factors that caused that hole in the graph. So now I can figure out, well, where would the function be if that hole wasn't there? What's the location of that hole? I can do that by plugging 1 into this function, the x plus 1 function. And I get 1 plus 1, which is 2. So we just calculated the limit. We figured out where the function was heading towards. We figured out if we took out that discontinuity, if we take out the whole, where is the function? So if we look back to our work, we couldn't just substitute 1 in for x in any of these lines because it would give us 0 over 0 there, it would give us 0 over 0 here. So that means for these functions, the way they're written, the function doesn't exist when x is 1. But once we remove those factors, the factors that are causing the hole in the graph, they're causing the discontinuity, we're left with this function, which does exist when x is 1. And since this is a continuous function that exists when x is 1, we know as x approaches 1, the y values must be approaching whatever the y value actually is of that function, which is 2. So let's try out what we just did with these two examples here. So we're going to find limits of a function algebraically from equations. And I'm going to show you the graphs just so you can see what they look like. But for these functions, you're not going to be given the graphs. So part A says find the limit of these values as x approaches -1. Well, if we look at this function is actually a continuous function. It exists for all values of x. So it actually exists when x is -1. If I plugged in an x value of -1, the function's right there at a y value of -0.75. And since it's a continuous function, as I approached an x value of -1 from the left, it would be approaching that point. As then I approached an x value of -1 from the right, it would also be approaching that point. So wherever the function is when x is -1, that's also going to be the limit. So for this one, to calculate the limit, all I have to do is substitute -1 into the function and see where it is. So do -1 squared minus 4 over -1 squared plus 3. So 1 minus 4 is -3. 1 plus 3 is 4, and I get that -0.75 value that you saw in the graph. Part B is a bit different because I can't just plug 3 into this function. This function actually isn't a continuous function. It has a restriction. X can't be 3. If x was 3, I would have 0 in the denominator, which means this is going to be undefined for an x value of 3. Over here, this one didn't have any restrictions, right? There's no way that could be 0. There's no possible way x squared plus 3 could be 0, so I didn't have to worry about any restrictions. I could just plug in the x value. But this one, I can't just plug it in. In fact, if I plug it in, I would get 0 over 0, which means there would be a hole in the graph at an x value of 3. But that does mean I could figure out where that hole is, and then know that the function would be approaching that hole from either side. Let me show you what I'm talking about on a graph. Okay, so here's the function. Notice there's a hole when x is 3. As I approach an x value of 3 from the left, it's going towards that hole, and as I approach an x value of 3 from the right, it's going towards that hole. So now I just have to figure out, well, where's that hole? What's the y value of that hole? We can see it's 4 by looking at this graph, but how are we going to do this algebraically? Well, like I said, I can't just plug 3 into this equation, because I get 0 over 0, which is indeterminate form. But what I can do is I can factor it. The numerator factors to x minus 3 times x plus 1. And then I can reduce this if I'm sure what I'm reducing is not 0 over 0. And because of this limit statement, I'm guaranteeing x is not 3. I'm just interested as x approaches 3. So if I know x is not 3, I know that this isn't 0 over 0. Therefore, something divided by itself is 1, and I can cancel them out. And what I'm left with is the limit as x approaches 3 of the function x plus 1. Now that function is just a continuous function. It exists when x is 3. So what I've done is, up here, I've removed the factors that cause the hole. So now what I'm doing is, I'm seeing, well, where would the function be if the hole wasn't there? So basically, where is the hole? What's the y value of the hole? Plug 3 into x plus 1. So I get 3 plus 1, which is 4. So the hole is at the point 3, 4. So I know the function must be approaching that hole from either side of it. So as x approaches 3, it's approaching the hole, which was at a y value of 4. So that's it for this lesson. I hope you have a decent understanding of limits now. And next we're going to be looking at Newton's quotient.